Hello students, welcome to this lecture number 5 on thermodynamics. In this lecture we are going to discuss some important thing in this thermodynamics chapter, that is extensive property and intrinsic property, as well also the heat capacity of the system, and some numericals we will also practice in this lecture. So let us write the heading of this video. This is Mukherjee in the Science with Mukherjee Sir YouTube channel. So first let us understand what we mean by the extensive property of the system. Extensive property of the system is such a property in which the value of the properties will depend only on the size of the system as well as the quantity of matter present in the system. So we can write this extensive property. Extensive property is basically depends on the quantity and size. Quantity of the matter and the size of the system. Example of these extensive properties is, that is volume, their mass, their internal energy, their heat capacity, or are the extrinsic property of the system, because all those will depend on the two things, that is size and the quantity of the matter present in the system. Okay. Then another property, that is the intensive property. Intrinsic property are those property value of which is not depend on, not depend on the quantity and size. Quantity and size of the system. This is called the intensive property. The example of the intrinsic properties are, that is pressure, for example pressure, density, temperature, specific heat capacity, or are basically the intrinsic properties. And if we analyze why it is intrinsic properties, we can easily understand one thing, that this quantity, that is the physical property of the system, do not depend on the quantity and size of the system. Now let us understand in depth how to distinguish these two properties. For this, let us take a container. This is a container. In this container you can see that it is having the gas. The volume of the gas is V and its temperature is T. Suppose we divide this container by divider with this fashion. This is divider basically, and in this division what we will find that in the both parts are equally being divided. At that time what we see, the volume of the gas in the container become halved, that is one half having V by 2 and other half having the V by 2. But at that time what we observe, the temperature will remain same. So you can see the temperature is same. Temperature do not depend on the size of this vessel, but volume depends. When we divide this volume into two parts, what we find that it will become V by 2 and V by 2. That is why volume is the extensive property. Volume is the extensive property, whereas the temperature is the intensive property, because it do not depend on the size and the quantity of the system. And we can convert this extensive property into the intensive property by specifying the amount of the substance. How? As for example, mass. Mass is a extensive property. Mass is a extensive property. Okay. Now this will become the intensive property when we specify the mass in unit volume. Specify the mass per unit volume, that is mass per unit volume will be the incentive property, because at that time the physical quantity is called the density. This is called the density, physical quantity, and this physical quantity do not depend on the mass, because we already specify the mass. So it will become the incentive property. So if the mass is the incentive property, then M by V, mass per unit volume, is density, is not the extensive property. It transforms in the intensive property. So we can understand what is extensive property, what is intensive properties, how to distinguish it, and how we can convert the extensive property into the intensive property by specifying the amount. Okay. Now we are going to understand a very important extensive property, that is the heat capacity, and some numericals we will do. Now we are going to discuss the heat capacity of a system. What is heat capacity? Heat capacity is represented by capital C. Suppose we want to measure the heat absorbed by a system. How do we able to measure it? Suppose a system, we have supplied some heat. Suppose Q is the heat. Then how do we able to measure this heat? This can be measured indirectly by checking the temperature rise of the system, because when we add some heat to a system, or we can say the system absorbs the heat, at that time what is going to happen? The temperature of the system will going to increase. So suppose the temperature increase is delta T. So we can write, because the amount of heat is proportional, or you can say that amount of rise in the temperature is proportional to the heat. So we can write this Q, that is the heat, is directly proportional to the del T, and this can be further written coefficient into delta T. And this coefficient is depend on the size, quantity and nature. Three things that is going to be the factors for this coefficient. And this coefficient is called the heat capacity of the system. So Q is basically, you can write capital C into del T. So here C is the heat capacity. This is called the heat capacity. So you understand what is heat capacity? Heat capacity is basically a coefficient. Now this heat depends on the size, quantity and nature of the system. Means if suppose the heat capacity is large, then what is there? What will be the physical interpretation? That we have to give higher amount of heat to increase a particular amount of rise in the temperature. So heat capacity higher means what? Now that will have, this substance will have the higher holding power of the heat, that we have to give higher heat for a particular temperature increase. So how do we define this heat capacity? Heat capacity can be defined in this way. It can be defined, we can write this. It can be defined the amount of the heat mass for a given mass is called the heat capacity. So you write the heat capacity in this fashion. The C is equal to Q by delta T. This is the heat capacity. Now, if this given mass is changes, suppose we specify this given mass, then it will be termed in a different way. That is, the specific heat then comes under point, specific heat capacity. Specific heat capacity. Specific heat capacity means we are specifying the amount of substance, and it can be written. Suppose the temperature has been increased from T1 to T2. Suppose we are increasing the temperature from T1 to T2, and the given mass, here given mass is not, it is 1 gram of mass. 1 gram of mass. So we can write the heat capacity when we want to increase the temperature of the 1 gram of the mass of the substance by 1 degree Celsius or 1 Kelvin, then the amount of the heat supplied in that case will be the specific heat capacity. So you understand what is specific heat capacity? Now it is the amount of the heat absorbed by the system which is having 1 gram mass, and the increase of the temperature is 1 degree Celsius or 1 Kelvin, then we will call it is the heat capacity. Suppose the mass of the amount is M. Suppose heat capacity is represented by small c. So we can write the Q is equal to M into del T into specific heat capacity. So you can just see what is the difference, specific heat capacity, and this the difference of the M. Here M is specified, here M is not specified. In this fashion, there is another important term, that is the molar heat capacity that we will understand. So we will understand the molar heat capacity. It is another very important term, molar heat capacity. It is being denoted by the Cm. Suppose a substance is having the n mole of substance. Suppose n mole of substance. N mole of substance, and this substance absorb the heat. It absorbs the heat, absorbs heat is Q. Then its molar heat capacity will be Q by N. So we can define this molar heat capacity for 1 mole of substance, the amount of the heat supplied, amount of heat required to 1 mole of substance, 1 mole of substance to raise the temperature by 1 degree Celsius or 1 Kelvin. It is called the molar heat capacity. Is there any correlation between the molar heat capacity and the specific heat capacity? Is there any relation? Yes, there is a relation. That is, molar heat capacity is a very important relation. You must remember, it will require during your solving the numericals. That is given by specific heat capacity, specific heat capacity into the molar mass. You can easily understand specific heat capacity is basically the heat capacity of 1 gram of substance, and when we divide into multiply it with the molar mass, it will become the molar heat capacity. Molar heat capacity. Okay. Now, what is a very important thing to understand? Heat is not a state function. So, heat capacity will not be a state function. So, whenever we say about the heat capacity, you have to identify the path, because it is a path function. The path means which condition we are taking this heat capacity. So, there is a 2 type of heat capacity. You can see heat capacity can be divided into 2 ways. Heat capacity of 2 types. Heat capacity is 2 types. What are the 2 types? Number 1, the heat capacity at constant volume. Heat capacity at constant volume. This is called CV. Another, heat capacity at constant pressure. This is called the CP. Heat capacity as constant volume and heat capacity as constant pressure. Now, what is the relation between these two? That we can able to understand. Heat capacity, we can write, suppose heat is absorbed, Q heat absorbed by a system, absorbed by a system at constant pressure, constant volume, suppose constant volume, volume. At that time we can write Q is equal to CV into delta T, right? And at constant pressure that will be QP. We can write CP into delta T, right? So we know one thing, that H is equal to U plus PV. We know this now. then you can write del H is equal to delta U into plus del PB. This can be further written in this way, that del H is equal to del U plus del into RT for n mole of gas. For 1 mole of gas. For 1 mole of gas, we can write this. Del H is nothing but the QP. So we can write here Cp into delta T. Here we can write U, internal energy change. You can write this Cv into del T plus del into R. So what we get? We get Cp is equal to Cv plus R. So Cp is always higher than Cv by R for the 1 mole gas. Suppose it is n mole gas, then it will be n into R. Numerical that you can see, 1 mole of ideal monoatomic gas is mixed with the 1 mole of an ideal diatomic gas. The molar specific heat of the mixture at equal volume is, we have given 4 choices. What you can do, we can pause the video and solve yourself. Think for a while, how do we able to solve it, right? At the same time, I am going to solve it. So what it wants, this numerical wants to know when the monoatomic gas and the diatomic gas has been mixed, then what will be the resultant Cv, that is molar heat capacity of that constant volume. So you know, first we have to know, that is the very important thing that you must remember, for the monoatomic gas, what will be the Cv for monoatomic gas? Monoatomic gas, the Cv, that is specific at heat at constant volume, is basically 3 by 2 into R. When you have to solve this type of question, that you will see the answer in which units is given. It is given in the calorie. So you have to put R is equal to 2. So Cv is equal to 3 by 2 into 2, that is as a 3. 3 calorie per mole per Kelvin. That is where. So 3 calorie per mole per Kelvin, that is to be the unit. We know Cp. What is Cp here? You do not have the Cp because you do not want to know the Cp, but you can calculate. If you add it with R, it will get the Cp. Cp will be 5. For the diatomic, Cv is 5 by 2 R. So it will be 5 calorie per Kelvin per mole. So what will be the resultant? Resultant molar specific heat at constant volume. Molar specific, that is resultant Cv, will be 5 plus 3 by 2, that will be 4. 4 will be the correct answer. So you can see, you have to remember the Cv for the monoatomic gas, Cv for the diatomic gas, that is, from that you can able to calculate easily. The average of these two things, that will be this mixture, molar specific heat at constant volume. Question number 2. 1 mole of an ideal gas for which the Cv has been given, that is specific molar heat at the constant volume, that is given by 3 by 2 into R, is heated reversibly at a constant pressure of 1 atmosphere from 25 degrees Celsius to 100 degrees Celsius. You have to find out that del H, enthalpy change. So first, at constant pressure means we have to go for the heat capacity for the constant pressure Cp. So Cp we know Cv plus R for the 1 mole of gas. Correct? So Cv is given 3 by 2 R, it is coming around 5 by 2 into R. Here one thing you can see, the answer is given in the joules. So answer is given in the calories. Okay, no problem. Answer is given in the calorie. But sometime when it will give in the joule, at that time this R will change. R will be 8.3. So it is given in the calorie. So what is given? What will be this? R is equal to 2. So 5 by 2 into 2, it will be 5. So we know what is del H. Del H is nothing but the Cp into del T. So Cp is already calculated and del T is 100 minus 25, that is 75. So it will be coming around 375 calories, and that will be the answer. Okay. Very good question that you can see that 0.06 mole of KNO3 is added in 1 centimeter cube of the water at 298 Kelvin. The enthalpy change of the KNO3 aqueous solution is this. This is plus 35.8 kilojoule per mole. And after the solute is dissolved, the temperature of solution. Then first you have to see the temperature will increase or decrease. If it is an exothermic reaction, then it will increase. If it is an endothermic, it will be water. So what is going to happen? You can see here the 35.88 kilojoule per mole. This is the endothermic reaction. And if it is an endothermic reaction, then it will take up the heat from where? From the surroundings, that is from the water. And the water value, temperature of the water will be decreases. So this first you have to see the how much is heat is absorbed from the water. That you can see from 0.06 mole into 35.8. This will be the number of kilojoule will be this. As a heat has been taken up by this, and that will be from where it is be taken up, from this water. So you can see water, 30 into water M, and is specific. And here one thing, that is it is in the joule. Here it is joule. So here specific heat we have to give you 4.184 into del T. So this will be equate, you can equate, and you can find del T is coming around 5 Kelvin. So the temperature will decrease and it will be this. Okay. Okay, that is all for today's lecture, and in the lecture we have discussed very important thing that will be helpful basically on the point of view of different types of numericals will come. Thank you very much for watching. If you like this lecture, I think this will be very much helpful to you. You can share to your friends, and thank you.